Let f and g be twice differentiable real-valued functions defined on R. If f prime of x is greater than g prime of x for all x greater than 0, which of the following inequalities must be true for all x greater than 0? Okay, so I think I'll probably just go through these one by one and rule out the ones which don't necessarily have to be true. So A is that f of x is greater than g of x. I mean, they're twice differentiable, and f prime is greater than g prime, but that has nothing to do with whether they're ordered in a particular way, so that's wrong. I mean, simple example, there's f and there's g. B, f double prime of x is greater than g double prime of x. This is also going to be wrong. So f always has to increase more than g. So that's f. And g will just be, let's say that, have a really strong, sharp second derivative there. Well, let's do it like this. Let's go like that. So g is never increasing as fast as f, but clearly there's positive second derivative there, whereas g has 0 second derivative, so that's not true. Option C, f of x minus f of 0 is greater than g of x minus g of 0. This is probably going to be correct. So the left-hand side is equal to the integral from 0 to x of f prime t dt, and the right-hand side is the integral from 0 to x of g prime t dt. If I take a difference of these, this is equal to the integral from 0 to x of f prime t minus g prime t dt, and we're told that this thing is always positive. So this whole thing is strictly positive as long as x is strictly positive, and that's equivalent to this. So this will be the correct answer, but why don't we go through some of the other options to verify why they're not true. Okay, the next option, f prime x minus f prime 0 is greater than g prime x minus g prime 0. So this, I don't think this has to be true either. Again, imagine that f is a straight line, so that these two derivatives are in fact equal. That makes this whole thing 0. So there's f, and g, let's just make it something like this. Okay, so that's positive and that's negative, right? Increasing, decreasing. So this difference then is in fact positive, but that difference is 0. So this is not going to be correct. And finally, option E. Ooh, man, we're just really taking it to limits here. Again, let's just take f to be a straight line. So there's the function f. So the left-hand side is 0. I just need this thing to be positive, which means I want a high value, or a low concavity at the origin, and ooh, I can't have this, I can't have that be positive with my example, because then they will, in fact, something would go wrong. Well, hold on, no, I can go like this. I can go So there's G. Positive concavity here, but negative or zero concavity there. So that difference is positive for some value of x, this one, and that's 0. So again, this option doesn't work. That's a counterexample that I've drawn. Yeah, option C is the only one that is true for all values of x. And given that the question is talking about derivatives and ordering on the derivatives, immediately it comes to mind when I see what's written for option C that this difference looks like an integral of a derivative, and so we can use what we're told about the derivatives within this integral to make a conclusion. Nothing too special other than that. Thanks for watching.